Great, thanks everyone for having a mood disorders researcher in the house here today. Okay, just move this over. Great. So I'm really excited to be talking about this topic. I do want to point out that as someone who has a name very similar to a very common AI-based household personal assistant, I'd say that my relationship with AI is complex sometimes. But today I'm going to be highlighting some of the ways in which AI could help mental health research. Again, this is by no means the only way that we need to be making advancements in this area, but it's a way that we all need to collectively be aware of and be involved with. So we know that AI has now become seamlessly woven into the fabric of our everyday lives. It is this unseen conductor that orchestrates a symphony of personalised content, ranging from things like the meticulously curated music and movie recommendations to the predictive text that anticipates our words before we type them. Now, we know that AI has been capable of tailoring our own experiences, often down to the smallest of details, and it creates this environment that feels distinctly our own. So we need to be thinking about how can we harness this level of personalisation to improve mental health care. So my name's Alexis, not Alexa, Alexis Whitton, and as co-director of a new NHMRC Centre of Research Excellence focused on depression treatment precision, I'm really passionate about understanding how AI can be embedded within research to improve our ability to tailor treatments and affect better outcomes. Now today, what I'm going to be doing is highlighting 3 ways that AI is already changing mental health research. I'm going to be highlighting some examples from the research that has been conducted within our Centre of Excellence. They do focus on high prevalence conditions like depression and anxiety, but they are incredibly relevant to the study of all mental health conditions, including psychosis. I'm also going to end today by describing the collective responsibility that we all share to ensure that advancements in AI actually help those who need better treatments, rather than hindering them or widening health disparities. And we need to ensure that nobody is left behind in terms of benefiting from these technological advances. Okay, so the first way that AI is now shaping mental health research is by enhancing our ability to conduct more efficient clinical trials. And this is something that we've been working on at the Black Dog Institute. Now, I want to step back for a second and describe the common way that new treatments for mental health conditions are studied in the research lab. Typically, the gold standard is the randomised controlled trial. Now, this is where individuals with a particular condition are brought into a clinical environment or laboratory and are randomly assigned to one of several different treatment arms. Now, in this context, people are usually equally assigned to either an effective treatment arm or a placebo or ineffective treatment arm, and this is done in an equal ratio. Now, when it comes to studying things, questions like what treatment worked best for who, the randomised control trial is not necessarily the most efficient way to study this or answer these questions, and there's several reasons. So typically, when you adequately power a randomised control trial to distinguish the effectiveness of different treatments, you are underpowered to determine whether different treatments work better than others in different subgroups of individuals. It's often impractical to enrol enough participants to be adequately powered to detect subgroup effects, and this is even more so the case when we think of lower prevalence conditions. In addition, randomised control trials assume that all treatments exert relatively homogeneous effects in terms of their variability, but this is often not the case. You can potentially get away with fewer people in certain treatment arms if that treatment has a relatively homogeneous effect. And I think what's most important is that it's more desirable in clinical trials to be able to skew randomisation to treatment arms that we think are really going to help and minimise the number of people who need to receive those placebo or ineffective arms. So an alternative to a standard randomised control trial is an adaptive trial. Now, instead of running one single trial, in an adaptive trial, you can run a sequence of mini trials. And over the course of these mini trials, you can use early results to alter the trial parameters based on incoming data. And here's why this design is particularly beneficial for understanding what treatments work best for who. So in an adaptive trial, you can prioritise randomisation to effective interventions based on incoming data. In addition, you can measure participant-level characteristics. So this could be somebody's demographic factors, their symptom profiles, their profile of side effects, their preferences. And then you can use this to examine how treatments work among different subgroups of individuals and alter your randomisation to different trial arms based on these characteristics. Now, this means that optimal treatments for people with certain characteristics can start to be identified earlier in the course of the trial. And critically, it means that fewer participants can be allocated to ineffective trial arms. Now, we've been exploring ways in which artificial intelligence can enhance this process. And in partnership with a team of AI specialists based at Deakin University, we've conducted the first AI-enhanced adaptive trial in the field of digital mental health research. This is called the Vibe Up trial. Now, the Vibe Up trial was initiated to meet an unmet need for low-intensity, easy-to-access treatments for university students experiencing psychological distress. And this is an umbrella term that refers to problematic levels of depression, anxiety, and stress that impact people's day-to-day life, and it can be experienced by anyone. Now, there are a range of different interventions that have been shown to be effective for treating or managing psychological distress. And we went through the literature and identified 3 of these interventions. So we identified brief mindfulness intervention as one that had been shown to be effective, physical activity, as well as sleep hygiene. Now, what was interesting about these interventions is that they were all interventions that individuals reported experiencing benefit from. They aligned with some people's preferences, but they didn't show any clear indication as to which intervention was best for individuals with different types of symptoms. So here is a trial design with 3 different treatments where we could really test whether symptom profiles impacted treatment response. And we also included a control condition in there called ecological momentary assessment, which is essentially daily mood monitoring as a comparator. So we conducted, over the course of a year, 12 sequential mini trials where we used AI to alter the randomisation of individuals to different trial arms. So what did we find here? So this is a schematic illustrating the primary results of the trial. And what we found was that different interventions worked better for individuals with different levels of symptom severity. So as you can see, physical activity was the leading intervention for individuals with mild psychological distress, but also those with severe levels of psychological distress. In contrast, no intervention outperformed another for those with moderate levels. Now, an important point here that differs from what we would have observed in a randomised control trial is the nature of the way in which participants were randomised to the different trial arms. So here you see the total number of participants who were randomised to each of the 4 interventions based on their severity subgroup. Now, what I want to point out here is that far fewer individuals were randomised to the EMA control condition. So this is the least effective intervention. And this is not something that we pre-programmed. This is something that was the result of the use of this AI algorithm. Now, we also calculated, well, if we had run a randomised control trial, how many participants would we have needed to enrol to detect the smallest significant effect that we observed in our trial? And we found that we would have had to enrol nearly 500 more people. And importantly, this would have resulted in over 5 times more people receiving that ineffective control treatment if we had run a regular RCT. So the point of this shows that AI can be used to accelerate our clinical trials, maximising participant welfare over the course of a trial and making trials more efficient. And we think about the implications of this for lower prevalence conditions. This is really critical. Now, these sorts of trials could help us accelerate our understanding of how different treatments impact individuals with different characteristics. We could use them to study the effects of different physiological and genetic markers, different symptom profiles, or different preferences on treatment outcomes. And we can also use these models for assessing how well established models of care work for individuals with diverse sociodemographic characteristics, which is a really important area. Okay, so the second innovation I want to highlight that AI has brought is an ability to enhance personalised support through digital technology. Now, AI has led to significant advances in our ability to monitor not only clinical symptoms, but also people's daily physical activity and daily patterns. Now, with some funding from the Wellcome Trust, we've recently launched a new project that looks at the capability of data collected through smartphone sensors and wearable devices for providing greater insights into the daily unfolding of people's symptomatic patterns as they engage in their daily activities. Now, to date, we've collected digital phenotyping data from over 8,000 individuals experiencing depression through smartphone applications that were designed with young people who have a lived experience of depression, anxiety, and stress. And we've identified, using AI and machine learning, different features in these digital data traces that map onto different types of symptoms. But we don't stop here. So the real benefit in capturing symptoms in people's everyday lives and contexts is the ability to paint a richer picture of how these symptoms impact daily functioning. We can use this incoming data then to develop what's called a just-in-time adaptive intervention. And this is an intervention that is delivered to a person to deliver therapeutic support that meets a need that they are experiencing in real time. And they have an option to receive that treatment or not. So the way in which this works is that we use digital phenotyping and other methods to continuously assess symptoms, daily activity patterns, and behaviour. Then once the AI model detects evidence of changes in behaviour that might indicate symptom escalation, it triggers an offering of a brief digital intervention straight to the user that they can choose to use and implement. After the intervention is delivered, symptoms are then assessed. We say, was this beneficial for this individual? This data is fed into an AI model. And then the information is then used to better understand what brief interventions are most effective for individuals and most appealing to individuals for helping them self-manage symptoms in their daily life. So AI-based adaptive interventions could significantly enhance therapeutic support for individuals with psychosis. So it has broad potential for tailoring things like the type and timing of lifestyle interventions based on real-time activity and sleep patterns. So we know things like physical activity, education can work, but we also know that people are most likely to read through that information when they're about to go to sleep at night, and it's not very helpful to be receiving information to take the stairs instead of the lift when you're about to go to sleep. Much more beneficial to have that if you're on your commute to work. Now, these interventions can also be useful for adjusting the intensity of support based on changing levels of clinical risk, as well as managing side effects of medication, and also titrating the amount and complexity of information that is delivered as part of an intervention. We know that it can often be very overwhelming, so really adapting that to individuals' needs is a big priority. And now the third and final innovation that AI is bringing is this ability to augment clinical trials and research studies with AI-generated patient cohorts. Now, this probably sounds like something out of a sci-fi movie, but it's actually a way in which data can be represented that has a host of benefits in terms of reproducibility and enhancing trial design. To explain how it works, I just want to step back 1 second and describe an example of how algorithms are being used to model complex symptoms and syndromes. So this is a study here that I conducted in collaboration with researchers at Harvard Medical School and Emory University. And what we did here is used an algorithm, so a mathematical model, to try and understand the mechanistic processes that underpin a certain type of symptom. So this symptom of feeling like everything is an effort. This is a really disabling symptom. It's a problematic symptom reported not only by individuals with depression, but across the board by individuals who experience mental health conditions. And what we asked is, we said, okay, this symptom presents so frequently across many individuals, yet responds very differently to different treatments from person to person. Is it possible to understand whether there are differences in the mechanistic drivers at a cognitive level that may be resulting in someone's sensitivity or feeling like everything is an effort and struggling with that motivational drive? And so what we did is brought a large sample of individuals with mood and psychosis spectrum disorders into the research lab, and we administered a task that essentially asked them hundreds of times, very unpleasant, but whether or not they would engage in an effortful action or an easy action in exchange for different outcomes of varying values and effort. And so over the course of this project, what we then did is developed a mathematical model to describe the different ways that people make effortful decisions. And we came up with a host of different models that captured variability in effort-based decisions. And then we looked at people's patterns of responding and patterns of decision-making and said, what model best describes this person's data? So this is completely independent of their diagnosis and clinical symptoms. And then we grouped individuals based on the different patterns that their data showed. And what we found is that individuals who adopted different strategies to engage in effortful decision displayed very different profiles of clinical symptoms and also cognitive functioning. And there's a QR code here linking to the paper in more detail. But I want to identify this study as an example of how an algorithm can be used to model a particular element of a condition. This model doesn't capture the whole person at all. It captures one aspect of a condition through a mathematical process. Now, if we expand upon this, looking at how advances in generative AI could transform this process, an emerging field is interest in using generative AI to create virtual patient cohorts, and even at the level of the individual, creating what is often termed a digital twin that uses data to model the effects of different disease processes or different patient cohorts. Now, the way this works is that different streams of data are taken either from existing clinical trials, cohort studies, or from individuals who enroll in new trials. That data is collated and generative AI models are used to generate a synthetic version of that data that differs from the actual data but behaves in the same way. So using these virtual patient cohorts opens up really exciting possibilities to enhance our research, both in the field of mood disorders treatment but also psychosis. So these are a couple of examples of how these virtual patient cohorts could be used. As I've mentioned before, one of the drawbacks of our major clinical trial approaches is that just about equal number of people have to be assigned to ineffective control conditions. What if we could model the effects of a control condition on a virtual patient cohort, saving the real effective treatments for individuals who are enrolling in those trials? Another approach is to expand the size of our existing samples using virtual patients mixed with the data from real patients, increasing the sample size so we can discover biomarkers that might predict response to certain types of interventions. And finally, with low prevalence conditions, we know that sharing data is a real way that we need to accelerate research, but it also poses issue in terms of privacy. So sharing virtual versions of data rather than real data could lead to progress here. So all this to say, we also need to progress cautiously and balance some of the risks, particularly around data privacy, bias and fairness. We also need to ensure that AI models are developed in a way that is transparent and explainable, and with input from those with lived experience, their families and clinicians. And I've outlined a few priorities here for AI-based research in psychosis and mental health more broadly, which I'm happy to discuss more in detail. But really what I want to highlight is that we need more government funding to support AI-based mental health research. We're currently risking a future where our most powerful AI tools are those that are personalising to maximise profit, not to promote health. And this is where we need greater investment so that we can see change. I'd like to thank my collaborators, and thank you very much.